All right, y'all. Today we're going to be talking about two new derivative rules, the product rule and the quotient rule. So both of these rules, they're more of just different types of functions we could see, two functions being multiplied or two functions being divided. We're really going to be kind of applying all of the rules we learned last time with basic derivatives. So let's talk first about the product rule. So the product rule is applied when I have two distinct functions being multiplied, so f of x times g of x. So the product rule states that if I have two functions being multiplied like this, then they are equal to the first function, so f of x, times the derivative of the second function, plus the second function times the derivative of the first function. So it's kind of like we're just taking the derivative of both functions and then multiplying them by the opposite reciprocal and separating them by that addition sign in the middle. So let's look at an example. So h of x, we have 3x minus 2x squared and 5 plus 4x. So just to make things easier, let's call our first one f and our second one g. So what would my derivative of f be? And I'm just going to take both of these functions' derivatives separately, and then I'm going to apply that product rule. So the derivative here would be 3x becomes just 3. Subtraction sign stays the same. 2x squared, 2 comes down to become 4. X to the first. Then right here, 5 plus 4x, 5 goes away. Plus sign is not there anymore because it's really just positive 4x. And then positive 4x becomes 4. Okay, so those are my original functions. These are my derivatives. Now, because this is f of x and this is g prime, this is g of x, this is f prime of x. So it's almost like I can just cross multiply them and apply that product rule. So h prime of x is equal to 3x minus 2x squared times 4 plus 3 minus 4x times 5 plus 4x. And we are lazy calculus mathematicians, so I can leave it just like that. Obviously, it's a multiple choice question. You don't see it unsimplified. Then you can go and simplify it by multiplying everything out. But typically, when we start getting into these higher derivative rules like the product and the quotient rule, you will see those final answers unsimplified like this. They might do small things, like they might multiply the 4 in the first term, but it just kind of depends. Okay, so that's the product rule. So if you notice, really, the actual deriving is really happening with our power rule, our constant multiple, constant rule, derivative of x, sum difference, all those rules we did last time. The final answer just comes from applying the product rule, but it's almost more like a formula we're plugging into than it is a derivative rule, or at least that's how it's always kind of felt like to me. So let's look at another example. So f of x is equal to 6x plus 5 times x cubed minus 2. So we have two functions being multiplied, so I know I'm going to be applying my product rule. So first function is f, second function is g. So let's derive each of them individually. So 6x plus 5 would just be 6, because x becomes just 1, plus sign stays plus sign, but 5 just goes to 0. Then x cubed minus 2, this would be 3x squared, and then minus 2 would just go away because it's a constant by itself. And then we're going to cross multiply. So f prime of x is equal to 6x plus 5 times 3x squared plus 6 times x cubed minus 2. Okay, nice and easy. Now, one thing I do want to kind of point out, and it's really the nice thing about this being the product rule and we're separated by addition, is does it matter if I flip-flop these terms? Like if I got 3x minus 2x squared and I wrote that one second, and I wrote 3 minus 4x times 5 plus 4x first? No, it doesn't matter. It doesn't matter if I flip-flop 3x minus 2x squared and 4, or 3 minus 4x and 5 plus 4x. Same for number 2. So the product rule is kind of flexible. You don't have to stay super stringent. It's always f times g prime plus g times f prime. Okay, you can switch the two sets of terms, and then you can switch the order of the full term because of addition. Addition is that operation that we can switch it back and forth, and it still means the same thing. It just always has to be original function times opposite original function's derivative. So f times g prime and g times an f prime. Doesn't matter kind of the order we write it in after that. So let's look at number 3. So number 3, we have g of s is equal to the square root of s times 4 minus s squared. So this one, we kind of have to do a little bit of thinking beforehand because, well, I can't take the square root of s right away, but I can change that to be s to the 1/2. Then I have my 4 minus s squared. Okay, so now I have my g and my f. So then derivative of s to the 1/2 is 1/2 s to the negative 1/2. 4 becomes a 0, negative s squared becomes negative 2s. Okay, then I can cross multiply. Boom and boom. So we get g prime of s is equal to s to the 1/2 times negative 2s plus 1/2 s to the negative 1/2 times 4 minus s squared. So a little extra work on this one first, but otherwise pretty straightforward. Okay. So last product rule example we're going to look at is number 4. So y equals 2x cosine of x minus 2 sine of x. Now, at first glance, you might be like, well, Mr. Arbone, these two functions are separated by a subtraction sign, so it's not the product rule. Well, it's a little bit tricky, but it's actually just this first piece, 2x and cosine x, that's our product rule. The minus 2 sine x, I can look at and I can derive separately because we're separated by addition or subtraction, so my sum or difference rule applies. Okay, so 2x and cosine x are my two functions being multiplied, 2x being my f, and cosine of x being our g. Same color would be confusing. So now we can derive both of those. So the derivative of 2x would be 2. Derivative of 2x would be 2. In the color, that makes sense. Derivative of cosine x, remember that cycle is negative sine x. Then we would cross multiply here. So for y prime, for our first part, we would get 2x times negative sine of x, so negative 2x sine x. Then plus 2 times cosine of x, so 2 cosine of x. Okay, so that's my first piece. That's my product rule. So this derivative, this piece right here, became all of this. Okay, that was just the product rule for that first piece of the function. Now I can derive that minus 2 sine x separately. So the minus stays the same. Okay, 2 sine of x, what's the derivative of sine? It is cosine. The 2 stays the same because of that constant multiple rule. So it just becomes negative 2 cosine of x. And that would be my final derivative. So just like before, when we're separated by addition and subtraction, we can apply our rules separately in our formulas to kind of go across. And you're going to start to see these more and more as we kind of get to these more complex and compound functions, is that you're going to start applying multiple rules. Might use the product and the quotient. Eventually, we're going to learn the chain rule. So a lot of these different derivative rules all at the same time. So it's really, really important that you really have a firm foundation understanding of functions, what makes something a function, terms, how we separate terms, all those sort of things, so you know which rules to apply when. Feel free to ask me about this more in class if you're like a little bit confused. Okay, so that is the product rule. The second rule we're going to really talk about today is the quotient rule. So product is for products, multiplication. Quotient is for quotients or division, fractions. So if we have d dx of f of x over g of x, that is equal to g of x times f prime of x minus f of x, g prime of x, and a little extra twist, all over g of x squared. Okay, so a little extra pizzazz. So some first things that you should kind of notice. Okay, product rule has addition because addition and multiplication kind of go together. Quotient rule has subtraction because division and subtraction kind of go together. Second thing is quotient rule starts as a fraction, ends as a fraction. Okay, so that should kind of help you differentiate between the two. The other big thing about the quotient rule, now with the product rule, I talked about how as long as it's original times, or one original function times opposite derivative, the order doesn't really matter. Okay, with the quotient rule, the order does matter. It has to be g of x times f prime of x minus f of x times g prime of x all over g of x squared. So to help remember this, we got a catchy little tune. So this is going to be our low function, and this is going to be our high function. So this is also the same as low d high minus high d low all over low squared. Okay, low d high minus high d low all over low squared. And you're like, Mr. Ibone, that just sounds like a bunch more randomness on top of everything else, which might be true, but it's a little bit of a catchy tune, and hopefully you think about it in the back of your mind. Another thing that you can think about is low kind of sounds like hose, and hose are always on the bottom or on the corners. Okay, don't repeat that. I was told it way back in the day in my math class, and it stuck with me to this day, so hopefully it helps you out. But let's actually apply the quotient rule. So first we're going to find the derivative of y equals f of x minus 2 over x squared plus 1. Okay, so just like last time, we're going to identify our f of x and g of x, but this time we're going to call it our low function and our high function to help us with our low d high minus high d low all over low squared. Once again, we're going to derive each, so 5x minus 2 would become just 5. X squared plus 1 would become 2x. Then we're still cross multiplying, okay, but we have to know which one comes first. So it's low times derivative of the high. So x squared plus 1 times 5 is the function that we want first. So x squared plus 1 times 5 minus high times derivative of low. So 5x minus 2 times 2x all over low squared. So all over the original function for low, so x squared plus 1 squared, just like that. Hey, let's keep going. So same as last time, kind of very similar structure to our product rule, but we just have to be a little more precise because order matters this time. So we have x squared plus 2 and 2x minus 7, so low is on the bottom, or la. High is on the top. So x squared plus 2's derivative would become 2x. 2x minus 7 would be just 2. Cross multiply. Once again, it's low times derivative of the high. So g prime of x is equal to 2x minus 7 times 2x minus x squared plus 2 times 2 all over 2x minus 7 squared. All right, another one, but this time we're throwing in trig. Is that going to make anything different? It shouldn't. Same rules apply even when there's trig, so low on the bottom, high on the top. Derivative of x cubed is 3x squared. Derivative of cosine of x is negative sine of x. Cross multiply. So f prime of x, remember our order, low times derivative of high. So x cubed times negative sine x minus high times derivative of low. So cosine of x times 3x squared all over low squared, so x cubed squared. And once again, y'all, you can simplify these if you want to. As we kind of start to get to these big old messy fractions, simplifying becomes a little harder. So you don't have to, but of course, if you want to, or if it's a multiple choice question, you don't see your answer there, you might have to simplify them. But we can be lazy. We can just leave it like this, and that is an acceptable answer. All right. Last but not least, number 8. Ooh, this one looks messy. We have x plus 2 times 2x minus 4x cubed all over sine of x. So this time, what makes this one a little bit more difficult? Well, we have two functions being multiplied in the top, and then we just have a normal function by itself on the bottom. So on the top, when we take the derivative of that one, what rule are we going to have to apply? Well, two functions being multiplied, so we're going to have to apply the product rule. So we're doing the product rule within a quotient rule. So this is where they start to get a little confusing. So you have to make sure you keep your rules in order. That's why I try to kind of show this really clear work, so you can kind of keep it straight in your head with, okay, I do the product, okay, and then I plug it into the quotient, okay, we're good to go. So let's actually check it out. So 8, we have our low function sine of x. We have our high function x plus 2 times 2x minus 4x cubed. Okay, so the derivative of the low function sine of x is cosine of x. The derivative of the high function, well, now I have f and I have g. F and g. So f is x plus 2 times the derivative of g, so times 2 minus 12x squared. Okay, and then g, so 2x minus 4x cubed times the derivative of f, which is just 1. Okay, so that was my product rule. Original f times derivative of g, and then g times derivative of f. Okay, now I'm applying my quotient rule. So cross multiply, it is low times derivative of high. So h prime of x is equal to sine of x times this old big old mess, x plus 2 times 2 minus 12x squared plus 2x minus 4x cubed. And I'm just going to drop the 1 because it's not really necessary. Minus high d low, so minus x plus 2 2x minus 4x cubed, 4x cubed. I'm running out of room. We're going to erase because I wrote too big. And times derivative of low, all over low squared. So all over sine of x squared. Okay, that one's pretty messy. So hopefully I don't ask you as a follow-up to evaluate the derivative at pi over 2 or something crazy like that, because that would be a mess to plug into. I mean, you could get asked that question, but likely if the derivative is as complicated as number 8, the only thing you're going to be asked to do is to find the derivative. Okay. So that is our product and quotient rules. The other rules we're going to talk about, I told you last time we were going to learn them, but they are the rest of our trig functions. Okay. Now, the one nice thing about the trig functions is that they are kind of related. So like, yay, that's exciting. The not so nice thing about the trig functions is that they're not as nice as sine and cosine. So our derivative of tangent is secant squared. Our derivative of secant is secant x tan x. Our derivative of cotangent x is negative cosecant squared x. And our derivative of cosecant x is negative cosecant x cotangent x. Like Mr. Arbone, those are gross. How am I ever going to remember them? Well, the nice thing, tan and secant all have to do with each other, just like sine and cosine have to do with each other. And then cotangent and cosecant all have to do with each other, and they're both negative, just like all the rest of them have to do with each other. So they kind of fall in pairs, which is nice. And all the rest of them, while gross, they are kind of similar. Tan becomes secant squared, cotangent becomes negative cosecant squared. Secant and cosecant both get the double ups. Okay. Now, a little mnemonic trick. Okay, I got all the tricks today to help you remember these. Is psst. So if someone psst at you, what are they usually doing? Well, they're probably asking you for help on a test, which we don't give each other help on tests because that's cheating. But psst can also help you remember your trig derivatives. So first of all, with psst, P's are silent. We learned that in the English language. All P's are silent, probably. Okay, but with psst, I know that the derivative of secant is equal to secant times tangent, and I know that the derivative of tangent is equal to secant times secant, which is secant squared. Okay, so that's kind of nice. Okay, now if you need to hear that again, okay, so it is psst, like you're cheating on a test. Okay, well, you're kind of cheating because you know your derivatives, but also not cheating because you should know your derivatives. Okay, P silent. Derivative of secant is secant times tangent. Derivative of tangent is secant times secant, or secant squared. Now you're like, Mr. Arbone, well, that helps me in one way, but it doesn't help me with the rest. Well, like I said, they kind of fall together. So just change tangent to be cotangent and change secant to be cosecant and make them all negative. Okay, C, C, and C. Derivative of cosecant is equal to negative cosecant cotangent. Derivative of cotangent is equal to negative cosecant squared. Okay, so they kind of all fall together. It's not a perfect mnemonic remembrance term. Once again, the thing that I learned a long time ago that I wanted to share with you. If you think of a better one, you let me know. I always love better ways to remember math formulas. But let's look at some examples. So we have number 9, y is equal to x minus tan of x. Okay, so this one, it's not product, it's not quotient, so I'm just going to apply my rules across. So y prime is equal to, x becomes 1, minus stays minus, tan of x becomes secant squared of x. Nice and simple. Okay, so yes, there's a bunch of new rules, but they're still kind of following through the same way we've always done. Okay, so 10, we have y is equal to x times secant of x. So this is a product rule. So now I got my f and I got my g. So derivative of f is 1. Derivative of secant is secant x tan x. A little weird that it becomes like two functions, but it's just what it is. Okay, cross multiply. We get y prime is equal to x secant x tan x plus 1 times secant x, so secant x. All right, number 11, we have 1 minus cosine of x over sine of x. So this is a quotient rule because we're dealing with the quotient. So we have our low function and our high function. So derivative of low sine of x is cosine of x. Derivative of high, 1 becomes 0. Negative cosine of x becomes positive sine. And then we can cross multiply, boom, boom. Remember, it is always low first. So low times derivative of high, low d high. So that is sine of x times sine of x. You can also abbreviate it sine squared of x if you would prefer. Then high times derivative of low, so minus 1 minus cosine of x times cosine of x. All over low squared, so all over sine squared. Okay? And last little one for practice. We got y is equal to cosecant of x minus cotangent of x. So it's not product, it's not quotient. So we're just going to derive across. So y prime is equal to cosecant of x becomes negative cosecant of x cotangent of x. Cotangent of x becomes negative cosecant squared of x. So negative cotangent of x becomes positive cosecant squared of x. And just like that, we've learned product rule, quotient rule, and all the rest of our trig functions. So many rules. If you're thinking, you're like, how many functions are there left? Well, we haven't talked about logs and we haven't talked about e's. So there are more functions. There's always more functions. Okay, last thing we're going to talk about today, y'all, is what we call higher order derivatives. Oh, Mr. Arbone had a typo. That's no fun. Ignore the confusing 95 right here. I'm just going to scribble it out because it's confusing. Okay, and what I mean by higher order derivatives is so far we've only been finding the first derivative, but we can technically keep taking the derivative forever. There's no limit to taking the derivative. We can derive over and over and over again until essentially we get 0, or with some of our functions like sine and cosine, they're just going to keep deriving over and over and over again in a cycle. Now, we're not really going to find like super crazy high derivatives, but you could find, the second or the third or the fourth or the fifth derivatives, and they do have some applications, which we'll talk about a bit more later on. The set of derivatives we're going to talk about the most this year is our position, velocity, and acceleration function. So we talked about this a bit last time, that if I take the derivative of the position function, okay, s prime of t, that's also the same as the velocity function. Well, if I take the derivative of the velocity function, that's not only the same thing as the second derivative of the position function, because now I've derived the position function twice, but it is also the same thing as the acceleration function. Okay, so position, velocity, and acceleration are related in this way, that velocity is the derivative of position and acceleration is the derivative of velocity. Wow, learn something new every day. Okay, things you've been doing for years, now you know where it all comes from. So let's look at number 13. We're going to find, so those three little dots, you guessed it, the third derivative. So find the third derivative of f of x is equal to x to the fifth plus 2x cubed minus 6x squared plus 7. So we're just going to go across. So f prime of x is equal to 5x to the fourth plus 6x squared minus 12x. All right, let's do it again. F double prime of x is equal to 20x to the third plus 12x minus 12. And f triple prime of x is equal to 60x squared plus 12. So you just derive, and you just keep deriving. Nothing too crazy to finding higher order derivatives. Okay, 14, we want to find f. It's not to the fifth, but it is the fifth derivative. So the fifth derivative of f of x is equal to negative x to the seventh plus 2 cosine of x. Well, this one's going to take a bit, but let's get to it. So f prime of x is equal to negative 7x to the sixth minus 2 sine of x. F double prime of x is equal to negative 42 x to the fifth minus 2 cosine of x. F to the triple prime of x is equal to, the 42 times 5 is 210, so negative 210 x to the fourth minus, not minus because cosine becomes negative sine, so plus 2 sine of x. So see how this term is basically just changing between sine and cosine, positive and negative? It's that cycle we talked about, how they just kind of go around in a circle. But let's keep going. So f to the fourth, you can do the 4 across, but usually once we get to 4 is where we switch over to the number. So f to the fourth derivative of x is equal to negative 840 x to the third plus 2 cosine of x, which brings us to the fifth derivative, f to the fifth is equal to, let's see, 840, 8 times 3 is 24, so 2400 plus 120, so 2520, negative 2520 x squared, and then minus again 2 sine of x. So as you can see, some functions like this one, we would keep deriving forever, eventually that first term, that x term, because as you can see, it does decrease in power every time as we go down. Eventually that would go away, but our trig term is never going to go away. It's always going to be there, just switching. As you can see, we cycled back to our first derivative's value there by the time we got to the fifth derivative. Okay, so let's kind of apply these ideas to 15 and 16, and then we are done for today. All right, 15, an automobile's velocity starting from rest is v of t is equal to 100t over 2t plus 15, where v is measured in feet per second. Find the acceleration function, and then find the acceleration at t equals 5. All right, we're finding the acceleration at t equals 5. So to get from velocity to acceleration, what do I have to do? I have to take the derivative. Also, we talked about this last time. What are we finding right now? Starts with an I. Okay, this is also instantaneous rate of change, okay, because I'm going to find the derivative, and then I'm going to plug into that derivative at a specific point in time. So this is IROC, except now you're starting with velocity and finding acceleration. Okay, so to find our IROC, okay, we need to take our derivative. This is a quotient rule, so we're going to be doing low d high, so low and high. Our derivative of 100t would be just 100. Our derivative of 2t plus 15 would be just 2. Then we're cross multiplying. So v prime of t, which is also a of t, is equal to low, so 2t plus 15 times 100 minus high t low, so 100t times 2 all over low squared, so 2t plus 15 squared. Okay, so that's my first piece. I found my acceleration equation. My second piece, I want to plug into it. So a of 5 is equal to 2 times 5, that would be 10 plus 15, so 25 times 100 minus 500 times 2. Once again, down on the bottom, that would be 25, but we are going to square that. So simplifying this out, we get 2,500 minus 1,000, not 100, 1,000, all over 625, which that would become 1,500 over 625, which, and you can, once you plug these numbers in, you can technically leave it and not simplify it all the way out. You know, another little trick for calculus, but we can also finish it all the way out. And if you do, we do get 12 fifths and our feet per second, so feet per second squared. All right, some practical applications of all the crazy derivatives we've been doing. Okay, I'm gonna let you all do 16 by yourself real quick. So I'm gonna pause the video, you can pause the video as well, and then check work here at the end. All right, also as you can see here, in our example, a car is traveling and then it stops on its brakes. So we were given the position function. We need to find position, velocity, and acceleration at t equals 2. So we're kind of doing like IROC for IROC for all the functions. So we already have s, but we need to find v and we need to find a of t. So s prime we get from deriving to get negative 16.5 t plus 66. S double prime, which is v prime, which is a, we derive that to get negative 16.5. Then we just plug 2 into all the 3 functions, and we get those various different values, which at S of 2, we've traveled 99 feet. At v of 2, we were going 33 feet per second, which is slower than the 66 feet per second, so that lines up. And then a of 2, the function was just negative 16.5, which makes sense. If we're braking, then we should be decelerating at a constant rate, right? So our speed should be going down at that same rate because we just slammed on the brakes and we're going down. So it's always going to be negative 16.5. All right, y'all, that concludes today's notes.